Okay, we're going to try this lecture one more time. Okay. So the big ideas of this section of chemistry are elements, atoms, and compounds, and chemical bonds. These two really are the ones that we're going to look at today, is just looking at atoms, elements, compounds, those things, and chemical bonds, which should be things that you already know something about. So remember to listen for the most part, and then if you need to write, a few things down, then do that. But let's try to get through it quickly and it not take you so much time. So elements, atoms, and compounds. Hold on, I gotta get out my little piece of paper here that says the essential question on it, because on the next one we'll write our essential question for this chapter. So EQ, well, what are electrons, atoms, and compounds? You probably could have come up with this yourself. What are electrons, atoms, and compounds? Okay, and then we say, and then how do they bond? I decided just to be lazy and not change the color of the background, and now I'm regretting it. But you have the essential question. It's kind of messing with my eyeballs right now, so I'm going to move it. Well, hopefully you don't spend too long on that when you write it as fast as I do. So, why do we have to learn chemistry as part of biology? Well, living organisms are composed of matter. You should know of matter from chemistry, which is just anything that occupies space, which is what we knew as volume, and has mass. So it has weight, but it just has stuff that makes it up. So stuff makes it up and it takes up space. That's matter. Matter is composed of chemical elements. An element is a substance that can't be broken down any further let's read the slide here. Hold on. Substance that cannot be broken down to other substances by ordinary chemical means. It is the purest that we can get it. Okay. In nature, there are 92 elements, and only a few really exist in a pure state. Some of the other ones on the periodic table kind of got made up because somebody could make them in the lab to fill that space, but really only that many kind of occur in nature. Alright, we have, in the human body, we have a whole lot of elements. Now, there are 4 of these guys that make up 96% of your body. And when we talk about these things in the coming chapters about carbon, nitrogen, hydrogen, and oxygen, these are a huge factor in carbohydrates, proteins, lipids, which are fats, and then even DNA. They're mostly made of these things, which is a good portion of your body, so it's made up of this. We do need other elements to stay healthy, and so in kind of percentage of body weight, calcium is really important. That actually helps with brain function. It helps with muscles. Calcium does a lot of good stuff. So do potassium and phosphorus. We also have sulfur, sodium, chlorine, and magnesium, and they all have super important functions in the body. They just altogether make up like 3.7. The other things that we have in the body are called trace elements. So you still need these guys, but in very, very tiny amounts. Okay, very tiny amounts. And you won't necessarily need to know those, but I'll just kind of show you how they're important here in just a few minutes. Okay, so a compound is a substance consisting of 2 or more different elements in a fixed ratio. And a fixed ratio like water is. So water is in a fixed ratio. There's always 2 hydrogen to 1 oxygen. So that's the fixed ratio part. But there's just mainly 2 or more elements. Okay. Compounds are more common than pure elements. Things just like to be stable. Okay, so pure elements are a little harder to find than compounds. Sodium chloride, that's table salt, is a really good example. And it's common part, it's in equal parts sodium and chlorine, so it's in a 1-to-1 ratio, but it's still at fixed ratio. It's equal parts. So sodium chloride is made up of sodium, which is a really just rough metal. It's super soft. You can cut it with a butter knife. But it's also really, really reactive. This guy reacts violently with water. You throw it in water, it explodes. It's pretty awesome. Chlorine, on the other hand, is a really like heavy, really toxic gas. It could kill you. Two things that probably are very dangerous and could kill you. But when they come together, they stable out, and they end up making something that's very tasty and delicious that we know as table salt. Love table salt. Okay, so about 25 elements are essential for human life, and we looked at some of those. Again, the 4 elements that make up 96% of the body are carbon, oxygen, hydrogen, and nitrogen. It's worth knowing those, but you might kind of remember, I don't know, Chon. Silly way, but those are the 4. And trace elements are essential, but are only needed in really minute quantities. So you still need some trace elements. Okay. So a couple of trace elements. One is iron, one is iodine. So iron is you need in tiny amounts, but it's a major component. So there's this interesting stuff, and it looks, I don't know, almost like a 4-leaf clover, but it's got some other stuff going on. It's a hemoglobin molecule. This is what transports oxygen in your blood. And so right in the center of it is where an iron sits. Now it looks like a flower. But an iron sits right there in the middle so it can grab the oxygen and then take it around the body. And so you need the iron in order to transport the oxygen. It's really essential. Without iron, we end up with what's called anemia. And it's potentially dangerous. So you need that. And also, by the way, if you cut yourself and you're bleeding, your blood has a metallic taste. It's because of the iron. The other thing that we have is iodine. So an iodine deficiency prevents production of thyroid hormones, and the thyroid controls so many of the hormones released in the body, which just tells your body to do things. And if you don't have that, it results in this thing called goiter. And you don't necessarily have to know that, but it's just interesting. And this woman has goiter. It's a huge swelling around the area where the thyroid is because of a deficiency in iron or iodine, which is why we usually have iodinized salt at the grocery stores. So there's a little iodine added to the salt, so that way we'll make sure we don't have deficiencies. Fluoride's another one that you don't need a whole lot of, but it's usually added to municipal water, and it's in toothpaste to help prevent tooth decay, because you've got to have fluoride to make sure your teeth stay nice and healthy. Okay, so it's in your toothpaste. And we like that stuff. It's good in there. It's weird, but it's important and we need it. Several chemicals are added to food to help preserve it or make it more nutritious or just make it look better. A lot of the reason that chemicals are added to food or different types of chemicals that wouldn't naturally be there are partly due to the consumers, to be quite honest. If we want it to look better, certain things are added so it stays looking better. That's the human on that one. So check out the nutritional fact labels on foods and drinks that you purchase. Okay, so like this cereal has, not that much, really not any fat, not much. It's not even a cholesterol, which we'll talk about as part of that category as well. There's a little sodium in there, potassium, there's some carbohydrates, quite a bit. And all of these vitamins, you can even see the iron, the trace element is listed here. There's enough for the day, some zinc and copper as well. So you can look at what things are available in foods. Now, I want somebody to look up peas tea and Cheetos and tell me how much nutritional quality is in those peas tea and then Cheetos. I just want to know. So we're right about 9 minutes, and we've kind of come to a different section. About every 10 minutes, I like to suggest that you guys take a break. And you don't necessarily have to, but it's just a thing I suggest. So this might be a good time to take a break, to pause the video and chunk your notes and write some questions. Whatever it is, about every 10 minutes, I'm going to remind you, like, hey, life exists outside of the computer right now. Okay? In the meantime, I'll keep going. So each element consists of one kind of atom. So a gold bar, as awesome as it is one pure kind of solid bar of one type of atom. It's pretty awesome. An atom is the smallest unit of matter that still retains the properties of that element. There are 3 subatomic particles that are relevant to our discussion. We should remember these, and we can write them shorthand. Protons, positively charged. Electrons, negatively charged. And neutrons are neutral. Okay? Simple enough to remember those. Neutrons and protons are packed into the nucleus. You should remember that one, is that those are both of the things that are found in the nucleus. The electrons orbit around it. Really just a thought here is the negative charge of the electrons and the positive charge of the protons keep the protons near the nucleus, or the electrons near the nucleus. There's debate on how all that works. But nonetheless, protons and neutrons in the nucleus, electrons around the outside. Okay. The protons give the atomic number. So that's what we have is the atomic number. And that really identifies that element. If you don't know that, if the atomic number changes, then the element changes. It's just that simple. So this is really the identification of that particular atom. Okay? The mass number is the sum of the number of protons and neutrons in the nucleus. Okay, because that's where all the mass comes from, is from these guys and these guys, because they're both heavy in the nucleus. The atomic mass is approximately equal to the mass number, but it's actually an average of kind of the regular stuff and the regularly occurring isotopes. So if you remember isotopes. If not, we're going to talk about them, don't you worry. Okay, so to reiterate, in the nucleus, like this is helium. We have 2 protons. We know they're protons because they have positives. And 2 neutrons. Those are nice and negative for us. So the mass here, we have a mass number of 4. Because we have 1, 2, 3, 4 things in the nucleus. Electrons, we have 2. And we know that it's electrically neutral because we have 2 negatives and 2 positives. And that gives you a 0. Okay. So although all atoms of an element have the same atomic number, so atomic number identifies the element, just to remember, they can have different mass numbers, and that's because of isotopes. So isotopes have, in case you don't remember, you should know, the same number of protons, but differ in the number of neutrons. So different isotopes of an element behave identically in chemical reactions. They behave the same because the neutron doesn't really do anything but give a little extra weight to it. And that, I mean, for something as tiny as an atom, it's not really that big of a deal. Okay. You do have radioactive isotopes. These guys are kind of interesting. And the nucleus decays spontaneous, giving off particles and energy. And I think I have a video that really shows this the best. It's actually like a Looney Tunes type video, which I'll show you guys. It's really cool. But what happens with radioactive isotopes is usually they're just big element, or like big atoms. There's a ton of protons, a ton of neutrons in the nucleus. And because there's so much in the middle, it's like having too many people in the room. Like they're just, it gets to be unstable. There's just too much going on. So the atom will actually kind of lose particles of like protons and neutrons, and it'll lose those things until eventually it becomes stable. So that's where those things, that decay comes from. Protons and neutrons just come off until it reaches stability. But like I said, I'll show you that one. It's interesting. So here's some isotopes of carbon. Most carbon is in what's carbon-12. It's got 6 protons, 6 neutrons, and 6 electrons. But the 6 protons and neutrons give it a mass number of 12. Not minus 12, but it's like an arrow. Alright, these... Okay, this one is carbon-13, and so it's got 7 neutrons, so its mass number is 13. We add those together, we get a mass number of 13. Carbon-14 is used for a lot of like carbon dating and things like that, and so we have 8 neutrons, 6 protons, and that gives us a mass number of 14. All of these still have the electron number of 6, and so they don't react any differently. My dog is trying to make a cameo. She doesn't get enough attention when I make videos over here. Alright, living cells can't distinguish between isotopes of the same element. And you don't necessarily have to write this, it's just kind of some interesting information, is that we can't distinguish between those. So we actually use some radioactive compounds as tracers. And so this radioactivity can be detected by instruments, and by using these instruments, the fate of radioactive tracers can be monitored in living organisms. And we use these, for example, in PET scans. So that stands for positron emission tomography. You totally know what that means, but no, it's just useful for diagnosing heart disorders and cancer and brain research, because we can see what the radioactive tracers are doing and where they're going. Okay, so here's an example of where we would see what's going on and where those radioactive tracers are going in the brain. Okay, so that's the interesting part there. Like, you could see the difference between a healthy person and someone with Alzheimer's. Okay, that's the interesting thing about radioactive isotopes. But it can also have its dangers as well. Uncontrolled exposure can cause damage to molecules, particularly DNA. We call those mutagens, and the chemical bonds can be broken. The scientists back in the day, like Marie Curie, who used to work with uranium, or radioactive uranium, she developed cancer later on and ended up dying from it, because that stuff will mutate. Okay? It'll mutate your stuff. We don't like that. Okay, so we're going to keep going here with chemical bonds. I like the bonding portion. It always makes me laugh. The only way I do these things is I have to think about relationships and people, and that's the only way I can make sense of it. If you've got some other way that you learned it that works best for you, you just keep with that. But I'll tell you how I know it. So the 3 subatomic particles, protons, neutrons, and electrons, only electrons are directly involved in the chemical activity of an atom. Okay? Only the electrons. So electrons can be located in different electron shells. Okay? And these each kind of have their characteristic distance or area from the nucleus. An atom may have 1, 2, or more electron shells, and information about the distribution of electrons is found in the periodic table of elements. We know, the periodic table of awesome. I love the periodic table. It's a design genius. By the way, this guy, just to show us, is carbon, and so we have 2 different levels, 2 different electron shells at work here, and we know that the outer one, we're just desperately trying to make 8 by any means necessary, so that way it'll be stable and happy. Okay? So here we get to look at it again, and we know, did we talk about valence stuff yet? We'll come back to it. Let's look at this. I think it's out of order. So the number of electrons in the outermost shell is called that valence shell, and it determines the chemical properties of the atom. So it's the stuff on the very outside that determines how it's going to react. So atoms whose outer shells are not full as in not 8, tend to interact with other atoms in ways that enable them to complete or fill their valence shells. Everybody's just trying to be stable, and if that means that they need a partner, they'll do that. Just whatever means necessary. And so just to show you, go back to this one, is these are the valence shells, or just the one on the outside. So these guys react chemically similar because their outsides all have just 1. Okay? Like beryllium and magnesium both just have 2 in their valence. Boron, aluminum, 3. So we get all the way over to fluorine and chlorine, which both have 7. Okay? And these guys have 8, so they're full and happy. That's why we call them the noble gases, because they really don't need anybody else. They're so noble. Okay? So 2 atoms with incomplete outer shells react. Each atom will share donate or receive electrons so that both partners end up with completed outer shells that equal 8. Okay? For the most part. The ones we're concerned with, it's 8. So these interactions usually result in atoms staying close together, and they're held by attractions called chemical bonds. Okay? And we'll talk about the bonds in just a second, but we are at 20 minutes, so it is a good time to take a break. So pause the video and then come back. And a covalent bond, and this one actually tells you about the words here. So think about co, like a co-worker or cooperate. It means we operate together or we work together. So it's kind of like together. So if I have valent, which is the valence shell, the outermost shell, it's the outermost shell are together. So this is where we share a pair of electrons. This is sharing. Okay. If two or more atoms held together by covalent bonds form, we get a molecule. So molecules are made of covalent bonds. Okay. And an example that connects two hydrogen atoms together is H2. So hydrogens have that one covalent bond. Okay. And that's the one exception to the 8 rule. Well, there's several others. It's fine. It'll work. Those guys have 2. Now we have all kinds of animations, and instead of kind of playing them here, we're going to talk about those and look at those in the next class period. So just hang tight for that. And I can make them available to you later as well if you'd like to look at them. There are 4 alternative ways to represent molecules. Hydrogens are held together by a pair of shared electrons, and in an oxygen, 2 oxygens share 2 pairs of electrons, forming a double bond indicated by a pair of lines. So 2 lines that kind of look like that. The thing about double bonds and triple bonds even is that they are a lot stronger. So the more things you share, the more things that work, right? The stronger it is. Trying to think here. So let's see. You and I, we share the class together, you know, like twice a week, right? So we share that. That's one thing that we share, is being in a classroom together and learning this stuff together. So maybe that's our single bond. Okay, so we're like hydrogen. Now me, and just because the dogs are over here and they're being funny, but the dogs and I, we share, well right now they're sharing the learning too because they have to listen to me do this. So they're sharing the learning with me, and then we're sharing a space together. We don't share food, but you know, I share food with them that I purchased. So we got a few more things that we share. So, you know, it's not offense to you, but I have a stronger bond with the dogs than I have with you. We've got a double bond there. Okay, so here are some examples how we look at them. There's molecular formulas for these 4. You could show the electron distribution around them to see how they share all these electrons. In each case, you could do the structural formula, which usually is how I like to show things, is with the structural formula. And you could use the space filling model, which gets a little crazy. It's the bigger the molecules that you get. Okay, but we're going to talk about it when we look at water here in a minute. Alright, hydrogen and oxygen are molecules composed of only one element, but we have methane, for example, and water are compounds or substances composed of 2 or more elements. Okay, so compounds consist of 2 or more elements. So it's a broader term than just molecule. Alright, atoms are in a covalently bonded molecule continually compete for shared electron, and so they have attraction or pull for shared electrons that we call electronegativity. Now I'll tell you what I call electronegativity. I call it like atomic attractiveness. And I mean atomic attractiveness and like how pretty that particular atom is. Some atoms are prettier to other atoms than others. Some are not so cute, some are real cute. All right, and then it follows so on the periodic table. So more electronegative, more attractive and pretty atoms will pull a little bit harder, meaning they take a little bit more than their fair share. In molecules of only one element, the pull toward each atom is equal because they only have one type of element. So the two carbons together will pull equally because they're both the same, which means they're equally attractive. They're both cute. So they're going to share completely equally because they're both equally attractive. So we share equal because they're both pretty. Or pretty to each other, whatever. A polar covalent bond means that we're going to share unequally. Okay, so we have different electronegativities. So like in water, oxygen just happens to be a prettier atom than hydrogen is. So because oxygen is prettier, it just says, look, I'm going to need a little bit more of these electrons than you most of the time, so I'm just going to have them. So we get what's kind of unequal sharing. It's like, that's nice, but I need these. So it has a slightly negative charge because that's also not very nice. But it's like, I'm prettier, so I'm just going to take these. Okay, so it's not very nice. It's unequal sharing. We call that a polar covalent bond because it'll create poles or two ends. I'll show you the two ends here in a minute. Actually, let's go to that while we're talking about it, and we'll come back to these guys. And then I'll go back. But if you see what's kind of happening here is like there's a slight negative charge on the oxygen and a slight positive charge over here because this oxygen's pulling the negative away from the hydrogen. It says, I need these electrons a little more than you do. It makes it a little negative and it makes those hydrogens a little positive. So we'll talk about that in more detail, but that actually creates where we can make some bonding with other water molecules. That's a special quality of water. All right. So basic things. All right, ionic bonds. So an ion is an atom with an electrical charge, and that comes from gaining or losing one or more electrons. So hopefully that's a review for you. If an electron is lost, if we lose the negative, then we have a positive charge. If we gain the negative, then we become more negative. Okay? Two ions with opposite charges attract each other. And when they attract each other, that's called an ionic bond. A salt is really a synonym for an ionic bond. So we could look there. Let's see. What really happens, by the way, when we talk about electronegativities and how attractive an atom is, these guys actually have really, really different electronegativities. Chlorine happens to be really pretty, and sodium is kind of ugly. There's my little face on that. It's kind of ugly. Have you ever seen a couple where one of the partners is really pretty, usually the lady, let's be honest, okay, usually the lady's pretty, and the guys are not so pretty. What is it that attracts them? Is it maybe money? And the fact that she, the pretty one, is taking his money? I'd say so. So electrons are kind of like money in this sense because she's real pretty. So she's going to take a little bit of his money. And he's like, that's cool because then we'll hang out together. Because you're pretty and I got monies. I got a little extra to give you. And that makes them both happy and they're attracted to each other and have a little relationship because it works. You know, whatever works for them. These guys usually form a lattice structure is what we kind of call this, and the fact that they'll alternate with each other because we got positive, negative, positive, negative, positive, negative all the way down. So they'll attract the opposite one. The last thing that we're going to look at really quickly is a hydrogen bond. And most of the chemical bonds are covalent in kind of molecules and things. So most of the strong chemical bonds are covalent, linking atoms to form a cell's molecules. Crucial to the functioning of a cell are weaker bonds. So this is going to be a weak bond that's actually between molecules. So one of the most important types of weak bonds is the hydrogen bond, and it's really the thing that makes water have all of its properties, which we'll get to talk about in the next class period. Okay, so hydrogen atoms of a water molecule are attracted to oxygen by polar covalent bonds. And we realize that because oxygen's a little greedier, so it becomes a little negative, like kind of negative, and hydrogen becomes kind of positive because it's nice enough to give away its electrons to that greedy oxygen. And because the way it does things, it just pulls in different directions, so it has a V shape. And so it'll have this kind of unequal sharing and then unequal distribution of charges. What we call a partial positive charge on the hydrogen and a partial or sort of negative charge on the oxygen. Okay, so hydrogen bonds are weak, and really we can, if you want to, you can come back, if you're into the reading thing, you can pause and take a look at that, but I want to move forward to the picture. I really do. If you need to go back, rewind it and pause and look at that, but I think it works better to show the picture. So we know oxygen is a little greedier and is taking more than its fair share of electrons, so it's slightly negative. The hydrogens are slightly positive. So it actually will kind of make friends with other molecules by those kinds of poles or ends. So the oxygen would be attracted to the positive portion of another hydrogen. The hydrogen over here is attracted to the negative portion of another oxygen within these molecules. And it's kind of a weak bond, and it moves around a lot and it changes, but these guys stick together based on this. And it creates a lot of their properties. Okay, so the negative parts of it will attract to the positive portion of a hydrogen, and then the hydrogen's positive will attract to the oxygen's negatives. Okay. So last little bit here is remember that the structure of atoms and molecules determine the way they behave. So structure of atoms determines how they behave. Atoms combine to form molecules, and that's via covalent bonds, because covalent bonds are what make them molecules. Hydrogen and oxygen can react to form water in our example here. So we've got hydrogens and 2 of them and oxygen, and that gives us water. And this is a chemical reaction. Hopefully we know that. You should be aware of that. Reactants are on the left side of the arrow. They're the things that we react together, so that would be hydrogen and oxygen. And water is produced, so it's our product. So it's on the right side of the arrow. Chemical reactions do not create or destroy matter. Okay, they only rearrange it. That's the key to that. Okay, so reactants, products, reactants, here we've got a total of 4 hydrogens and 2 oxygens, and they come together and still form 4 hydrogens and 2 oxygens. It's just rearranged of the bonding. Okay, and to give you an example, photosynthesis is a chemical reaction that's essential to life on Earth. Carbon dioxide from the air reacts with water. Sunlight powers the conversion of these reactants to produce glucose and oxygen, and we get to talk about that more than we want to later on in the semester. So with that, we'll be done. We'll talk about water's life-supporting qualities, all these cool things that it does, a little later on. So my apologies for the delay here on all of the issues, so this should work much better. If you have any questions, shoot me an email. Just keep working.